This is Probability and Statistics. We are in our penultimate lesson for this series. We are in chapters 12 and 14, specifically just the first section of each. And so, as always, I would encourage you to peruse the book Elementary Statistics 4th edition by William Navidi if you'd like to see what else is in those chapters. Specifically, we're going to be looking at, in chapter 12, what is called the goodness of fit test, or chi-square test. And in chapter 14, we're going to look at what's called the one-way analysis of variance, or more often called ANOVA. These two tests, like we've been looking at in the last few lessons, just deal with more hypotheses tests. And so these are just special cases where, in the past we looked at one sample, two sample. And now here we are going to look at situations where we have data and some kind of typically a claim, a distribution that we're comparing against to see if our sample shows evidence for or against that particular claim being made. There are other types of tests like these. In fact, chi-square, for example, this is, like I said, the goodness of fit. There's also what's called the chi-square test for independence and the chi-square test for homogeneity. But we're just focusing on this particular one for this lesson. So with that, let's go ahead and get going and see what this looks like. So we're going to start with the goodness of fit. And again, this is a situation where at least examples we're going to look at are situations where we have some kind of expected outcome. And we've taken a sample and we want to check whether or not our sample matches the expected values within some kind of level of statistical significance. Okay. So for example, it says Carrie made a 6-sided die in her ceramics class and rolled it 90 times to test if each side was equally likely to show up. The table summarizes the outcomes of her 90 rolls. So she makes this die, wants to see if it's balanced. She rolls it 90 times, and we can see the frequency of those rolls. So she rolled a 1 13 times, a 2 24 times, and so on. So just looking at that data, if we're kind of asking the question, is this die fair? Is it balanced? It would appear that maybe it's not. The 2 is definitely showing up more often than the others, and it seems to be showing up a lot more than the others. The question is, when we look at this from a statistical standpoint, do we have that convincing evidence that we've seen before to make a claim that her die is in fact not balanced? All right. So the first thing we need to do is we need to look at what would be expected if this was balanced. So if she rolls it 90 times and each side is equally likely to show up, our expected value here would be 90 times 1 over 6, or 15. So I'm going to expect that a 1 would show up 15 times, a 2 would show up 15, and so on and so forth. So these are my expected values for this problem. And so again, the question is, are her results close enough to those expected values for us to have evidence that, convincing evidence that her die is in fact balanced? And for this, we're going to use alpha equals 0.05 or 5% like we often do. All right. Now, I'm going to show how to do this by hand. I will be honest, this is the only time I would ever show by hand, and I would never do it by hand again. But I think it's important sometimes to see the math behind the formula or the function. After this, I will show how to use Excel specifically to do a chi-square test. But of course, any software program that does statistical work, graphing calculators, things like that could also do the same work for us. Before I get into this, let me just maybe clarify. We're talking about what's called a chi-square test. Chi-square, Greek letter chi, is simply a critical value. So this is a critical value, just like T or Z. So just like the hypothesis test that I've shown in the past, what we're going to do is we're going to find this chi-square value, just like we would find T or Z, and we are going to look it up in a table, just like we would T or Z, and that table is going to give us a p-value, and we're going to use that p-value to test whether, to determine whether or not we have that's convincing evidence. Okay, so again, other than the fact that the math behind this is a bit more involved, the overall process is very, very similar to any of the other hypothesis tests that we've looked at to this point. Okay, so we've got this table in front of us, this chart, and we're going to fill this in. And what's going to happen is the very, very end, we are going to add this last column. And when we add this last column, that is going to give us the chi-square value. So we have the observed values from our table previously, the 13, 24, 11, 16, and so on. So I'm going to write those in, 13, just forgot them already, 24, 11, 16, and 12 and 14, I believe were the last two. Let's double check that. Yeah, 12 and 14. Okay, so those are the observed. The expected, again, that was 15 all the way down. We would expect equally likely outcomes. Out of 90 rolls, each one would show up 15 times. Next, we're going to find the difference of the observed minus the expected. Now, I guess technically it doesn't matter if you put these as positive or negative because we're going to square them anyway. But just for consistency's sake, I always do observed minus expected. So I'm going to do -2, 9, -4, 1, -3, and -1. Again, if you just wrote 2, 9, 4, 1, 3, 1, you're going to end up with the same result because we're going to square these now and they're all going to come out positive anyway. Okay. And then the last step is to take that squared number and divide it by the expected value. So we're simply going to take all of these numbers, 4, 81, and so on, and we're going to divide them by 15. Okay, etc. I'll just show the first two. Obviously, we'll just do that all the way down the line. And so I've pre-populated these numbers, so I'll just write these in: 0.267, 5.4, 1.067. One thing I will say is be a little careful not to round these numbers too much, just so that you don't end up. Did I miss a number in here? I think I missed a number in here. 2.54, 1.067. Yep, I did miss a number because it's the same number above, just without the 1. 0.067, and then 0.6 and 0.067 again. So as I was saying, just be a little careful not to round these too much. We want to have a somewhat accurate chi-square value. So like I said, we're going to add these all together. And when we add these together, we get 7.468. And this is our chi-square value. This is that critical value now that we're going to look up in the table to find P. Just like T, we need a DF here. So DF is in this case, remember DF in the past has been the sample size. In this case, DF is the number of categories minus 1. And so by categories, in this case, we would just mean the 1, 2, 3, 4, 5, and 6, the outcomes that are possible. So in this case, we'll do 6 categories minus 1 gives us a DF of 5. All right. So I'm going to jump to the table here and show you how this looks. So this is what the chi-square table looks like. Again, looks a lot like the other tables we've seen before, the T and Z and so on, specifically like the T table. We've got the probabilities across the top. We've got the DF down the side. And so again, what we are going to do is find our DF of 5. We are going to go across that row. We're looking for 7.468. That was our chi-square value. And 7.468 falls right here between these two numbers. So our p-value is somewhere between 0.15 and 0.2, which obviously is well above 5%, and so we'll make our conclusion in just a moment. But that's how it works by hand. You find chi-square by hand through that somewhat elaborate process. I wouldn't certainly want to do that if I had a sample size of 50. We come to this table, we find our DF, go across, find chi-square to get the P. Again, just like we would do for T. So we've got P between 0.15 and 0.2. And again, that's from the table, which of course is, as I mentioned, greater than 0.05. And therefore we fail to reject the null. Okay. In this case, of course, the null being that the die is balanced. So in other words, we don't have evidence that it's imbalanced. So even though that 2, even though we kind of had this question about whether or not it's balanced because of that 2, we don't have evidence to show that it's imbalanced. Okay. If I was the ceramics teacher, I'd have to give her an A for the project. All right, we'll formalize this in a minute. But what I want to do is before we formalize the process, I want to jump to Excel and show you how we would do this in Excel because it is so much easier. So I'm in Excel. I've already pre-populated my sheet. You'll notice that in column A, I have my actual data from the sample. In column B, I have the expected values. So that's all you need to do a chi-square test in Excel is just simply put in your actual values and your expected values. They can be in columns or rows. It does not matter. And what I'm going to do is just in some blank cell, I'm going to hit equals CHI SQ for chi-square. And you'll notice that I've got a few different options here. I want the chi-square test. So this is ultimately what I want is the chi-sq dot test. And what it's asking for is where are the actual data values and then where are the expected values. So my actual values are in A1 through A6, comma, and my expected values are in B1 to B6. I'm going to close that out and hit enter. So that's all you have to type. chi-sq.test, where are your actual data values, where are your expected values, and when I hit enter, that's my p value. So this is p. All right, which is consistent with what we found in the table. Remember in the table we said it was between 0.15 and 0.2. That certainly is. Okay, so that's all you have to do for Excel. Type in that data, type in the chi-square.test, and that is easy as that. All right, so let's formalize this process and talk then about the steps that we would do for a goodness of fit test. As with any other hypothesis test, we do have assumptions. In this case, again, we always want a random sample. That's key to any of this. In this case, we also want all of the expected values to be greater than or equal to 5. In our case, they were all 15. We would be good there. So you always want to check for those two things. Is it random? And are all of your expected values greater than or equal to 5? Then you state your hypothesis. Again, as before, we have a null and we have an alternative. The null, now, typically in the past, when we've looked at the 1 sample, 2 sample test, we would have some kind of a singular value, and we might say that the mean is equal to 27, and the null is the alternative is greater than 27 or less than 27, something like that. In this case, all we're really saying for the null is something to the effect that the claim is true. Now, we'd probably want to include some context in there. We'd probably want to talk about what claim are we talking about. We might even include what the values are. But it's really more a matter of just our null is believing that the claim is actually true. The alternative then is that the claim is not true. So in our example that we just looked at with the die that was made, our null might be something like the die is balanced. That would be our null hypothesis. We might even say then that P1 is 15, P2, or excuse me, that outcome 1 is 15, and so on and so forth. And then the alternative would just be that it's not balanced. Okay, so it's almost more describing versus giving actual values when we make these hypotheses. We compute the expected frequencies. Now I'm going to give a formula here. So if you're doing this by hand using that chart, really what that chart does is it took the sum in that last column of the observed minus the expected squared and divided it by the expected. So you would do that for each value, add them all together, and that's going to give you chi-square. So if you want a formula, if you want to do it by hand, that's how you find chi-square. And then in to find the test statistic, to find the p-value, or excuse me, that is I think I skipped a spot, didn't I? I'm sorry. This is actually the test statistic. That's down there. The expected is just the sample size times the proportion for each category. Sorry, I missed a step there and got myself a little confused. Okay. So again, for our situation with the die, every single category had the same proportion of 1/6. We would expect every face to appear equally the same, or equally likely to appear the same number of times. Not always the case, though. You might have a situation where those frequencies are different or expected to be different. So you just take the sample size by the proportion of each of those. And you do that for every category. Those are your expected values. All right, we've got our test statistic. Now we go to the table to find P. Again, we would need DF. So this is the DF. And again, it's number of categories minus 1. All right, and that would give us then P. Okay. Now, obviously, these two steps, you would do that if you're doing this by hand. If you're not doing it by hand, right, so this is by hand. And if you're not doing it by hand, which I would certainly recommend that you don't, if you're using particularly Excel or Google Sheets, they both use the same function, chi-square dot test, chi-sq dot test. And then again, they just want the range of the observed or actual values and the range of the expected values. All right, so that's how you'd use, again, Excel or Google Sheets. Obviously, other programs would do the same thing, just have different protocols for how you would handle that. And then finally, we state our conclusion. So again, we would either reject the null or fail to reject the null, and then talk about the fact that we either do or don't have convincing evidence for whatever the claim is. Okay. All right, so let's do another example. Kind of put this all together in a more formal way then. So we're gonna do one where we do have different proportions for each category. We're going to assume that Mars Inc. claims that this is the distribution for the colors of their M&M candies. So again, this is not necessarily true. Let's just pretend, for argument's sake, that they claim that 13% of their M&Ms are brown, 14% are yellow, 20% orange, and so on. So we take a very large sample. We're going to sample 1,300 M&Ms and record how many of each color are in that 1,300 M&M batch. And these are the results. So of those 1,300, 160 were brown, 191 yellow, and so on. And the question is, does our sample give evidence to the claim that Mars is making? Does our sample show or give evidence to the fact that that is actually the distribution of M&M candies? Or do our results reject that claim and give evidence that it's something different? All right, so in order to do this, we are going to first of all do our check. And again, I should mention, let's set this at 0.05 again for alpha. So we have to check our assumptions. Again, we want to make sure we've got a random sample. In this case, we do. So we've got a random sample. And then secondly, we need to make sure that all of our expected values are greater than 5. Now, I will show this formally in just a minute when we get into Excel. But the other thing is, if you look at the data, we have very large numbers of samples here. We've got 160 brown. In fact, that's the smallest one. It also matches up with the smallest percent of 13. If I take 13% of 160, I'm well over 5. Everything else is going to be even bigger than that. So even from that, just from that inspection alone, we know that all of our expected values are greater than 5. But we do want to make sure that that is true. Okay. And again, when we get to Excel, I'll show you that clearly they are all greater than or equal to 5. All right, we've got our hypotheses, our null. So in this case, it would just be that the claimed color distribution of M&Ms is true. And the alternative is that the claimed color distribution is not true. Is not true. Okay? All right, so like I said, you are welcome to do this by hand if you'd like to. I'm going to go to Excel and I'm going to do this in Excel. So in this case, I have to type in some data here, and I'm going to show you just pretty straightforward, pretty basic, but we have to find the expected counts because what they gave us was not the expected values. They gave us the proportions for those colors, and we can't use proportions. We have to use actual values. So what I'm going to do is I'm going to start by just typing in the what we did find in our sample. We'll start with that as our first column. And then after that, I'm going to type in the proportions. And then I'm going to show how to just kind of deal with this. Now, when I type in the proportions, I want to type these in as decimals, not percents, because I'm going to use these along with the sample size to just quickly punch out the expected values then. All right. So those are the actual proportions. And in this case, then, what I'm going to do is remember our sample size was 1,300. So I'm going to say equals this proportion times 1,300. And that's our expected value for brown. And all I have to do is just drag this down now, and that's going to give me all of the expected values. So this is what I would expect to see for each of the various colors. And so you can kind of see already that, in A, we have what we got from our sample. In C, we got what we'd expect. They actually look fairly similar. I don't see a lot of real huge disparity in those numbers, maybe a little bit in the fourth one, which is green. But who knows? So we're going to run the test here. So we're going to find our p-value, again, equals chi-square dot test. Whoops. Equals, let's try that again, chi-square dot test. I'm just going to go down and grab that. And in this case, again, our observed or actual data is in A1 to A6. Be careful, or don't choose B now. Make sure you jump over to C. We want C1 to C6. And in this case, wow, we get a really, really, really small p-value, don't we? We get a p-value of 0.0002 if we round that, okay? All right, so let's head back to our notes here. So using Excel, right, we did the chi-square. I always like to document what I did to actually get these values, right? So here, I'll just say observed expected here, right? Because who cares? Nobody's going to know if I put it in A or B or whatever, right? But this is what I did in Excel. And that produced for us a p-value of 0.0002, which is clearly less than 5%, okay? So because of that, we actually reject the null. I'm a little surprised by that. Looking at the data, I would not have expected this, but we reject the null. We have convincing evidence. We have convincing evidence that the color distribution, or I should say maybe the claimed color distribution, right? That the claimed color distribution is not true. Now, again, this is all made up. Don't call or write Mars and complain about their false advertising. This is all completely made up. But there's clearly something in the data, something in the difference that was enough for us to come to that conclusion. Okay, so that's how we do a chi-square test. So we're going to do this one more time. And as always, I encourage you to, pause the video, try this one, make sure you really have it down, and then start it up, and I'll walk you through that. So a grocery store sells 4 different sizes of popular brand of cornflakes. For the past few years, the proportion of boxes they sell of each size has been quite stable. They give us those percents. The owner decides to change the pricing of the 4 sizes and wants to know if this changes the proportion of boxes they sell of each size. A few weeks after changing the prices, the owner takes a random sample of 120 transactions involving cornflakes and counts how many boxes of each size were sold. Here are the results. We've got how many were sold. And again, what we're looking for is basically whether or not changing the price actually changed the distribution of sales. All right, so our checks again, we want to make sure. Actually, no, before I do the checks, this is a very, very small sample size and pretty easy percents to work with. So let's do the expected value first on this one. In fact, I probably won't even go into Excel for this one. Expected results on this, let's see, 10% of 120, that's our sample size, is 12. And then next would be 18, 15% of that. 60% is 72. And back to 15%, which again is 18. So those are expected values. Obviously, then as we go through our checks now, as we get into the actual process, we do have a random sample. And we can clearly see that all of our expected values are greater than or equal to 5. So we're good there as well. All right, we have our null. Our null then, in this case, again, he changes the price, wants to know, did the price change the sales of his cereal by size? So our null would be that it didn't change, right? That the distribution of box sizes sold did not change. And then the alternative is that they did. So distribution sold, I'll just say distribution sold changed. We get the idea. Okay. So that would be the hypotheses. Now again, if we are to use Excel, I'll just remind you one more time, we're looking for chi.sq.test. We throw in our observed, we throw in our expected, and that's going to give us our p-value. In this case, you should get a p-value. If you go into Excel and just check this out, test it on your own, you should get a p-value of 0.023. And in this case, then, that is less than 5%, 0.05. And so we reject the null. We have convincing evidence, or there is convincing evidence, however you want to say that. So we have convincing evidence that changing the price or changing prices changed the distribution of sales. Okay. All right. So that is the chi-square test. Let's move on now, and let's talk about the one-way analysis of variance, or ANOVA, that is in chapter 14. So this is a little bit of a different type of hypothesis test. This is one that we can use when we have 3 or more populations, and we want to compare those populations against each other. Now, what this test does is it simply tells us if the means of at least 2 of the populations are statistically significantly different from one another. It could be that one population is significantly different from the others. It could be that multiple populations are significantly different from each other. So we don't get a lot of detail from this. We just know that there either is or is not at least one difference in those populations. So let me read the example. I'm not going to go through kind of the formal steps. We'll see that as we just go through the example. There is one slightly unique check that we have to talk about, but I'll do that, like I said, as we go through the example. Also, when we get to Excel, there is a setup that you have to do if you've never done it before in Excel, and I'll show you how to do that as well. All right, so it says a farmer wishes to test the effectiveness of 5 different fertilizers. He divides his land into 20 equal 1-acre sections and applies each fertilizer to 4 randomly selected areas. At harvest time, he records the bushels of corn produced in each section. Here are the results. So basically then, as you can see, we've got 5 different fertilizers, A, B, C, D, E. Each one of those fertilizers is used in 4 different areas of his farm field, so they can get a sampling and not just one section. And we've got the mean then for that section. We've got the standard deviation. The mean and standard deviation are not needed to do the ANOVA test. They are needed to do what is called the Tukey-Kramer test that we're going to do afterward. We're not going to do it for this example. We'll do it for a later example. As I mentioned before, you can't know whether or not, like in this case, is A statistically different from B or C or D or E? Is it E that's different, right? We don't know that when we do the ANOVA test. We just know that there is or isn't a difference. There's a test called the Tukey-Kramer test that allows us to drill into that detail and determine which populations are different from the others, okay? And that's where we're going to need sample mean and standard deviation. So that's why you kind of see it given with the data that we have for each of the examples that we'll go through. Okay, enough of that. Let's get into Excel and let's talk about how to use Excel for this. So when we set up our data in Excel, you'll notice I've got it pretty much set up like the chart in the notes. I've got the 5 fertilizers, A, B, C, D, E. You don't need to have the labels in A, but you can if you want to. And despite the fact that the table that I showed earlier just had kind of all the numbers in a single cell, you want to make sure that your numbers are actually in different cells in Excel, okay? So I've got my data in, and in this case, I happen to just have them by rows. Now, before I run the ANOVA test, again, if you haven't done this before, there is an add-in that you have to load in Excel in order to do this. So when you're in the data tab, so across the top, very, very top here, you've got home and insert and all of that. There's a data tab. When you click on the data tab, off to the very, very right, you want to see data analysis. If you do not see data analysis, you have not yet loaded in that add-in. If you see data analysis, you're good to go, all right? So let's assume that you do not have data analysis, and let me show you how to get data analysis. What we need to do is we need to go over to File. So in the very upper left corner of Excel where we've got File, we're going to click on File. And down at the bottom of that left-hand list, way down at the bottom is Options. So you want to be in the very lower right. You want Options, and it should pop up a window that looks something like this, okay? And again, down that left-hand menu list, second from the bottom is Add-ins. That's what you want to pick. So we're going to pick Add-ins. Now, I've already got mine obviously loaded in. It's called Analysis Tool Pack. If you are using Google Sheets, it's called XL Miner, M-I-N-E-R, Analysis Tool Pack. I think in Google Sheets, if you just start typing in Analysis Tool Pack, you'll find it. Okay, so you want the Analysis Tool Pack. Notice that there's also, I've got one that's inactive called Analysis Tool Pack VBA. That's not the one you want. You just want regular Analysis Tool Pack. Obviously, yours would be down here in the inactive. Find that, and then you just go ahead and install it, okay? Once you install it, when you go to the Data tab, again, you should see the Data Analysis option here, okay? All right, so we've got our data. We now hopefully have data analysis. I'm going to click on data analysis, and this gives us a whole bunch of different statistical analyses that we can do. Some of these, like you go down to the bottom, there's the t-test 2 sample, t-test 2 sample, t-paired. These are all things that I talked about in the previous lesson. So it can do that if you have the data analysis tool pack installed. But we're going to do the very, very top one called ANOVA single factor. So I'm just going to highlight that if it's not already, click OK. And it brings up a window. And what it's going to ask for, yours is probably blank. I was doing this earlier, so I've got some input range already in here. But in the input range, we want to select all of the data values for this. So if you did A, B, C, D, E, and you want to include that as part of the analysis, you're going to highlight all of that. Just make sure that 2 things are clicked here. First of all, if you did yours by rows, you want to make sure that it's grouped by rows, not columns. If you did it by columns, then obviously make sure that columns is clicked. And then if you are going to include A, B, C, D, make sure that you click labels in the first column. Okay. If I don't use that, if I just did B through E, I would uncheck the labels in the first column. We can also select our alpha value. Let's just assume 0.05 for this example. And then finally, you can choose where you want your data to be outputted. In this case, it defaults to new worksheet. I'm going to do new worksheet. It'll just create another tab within this workbook, and that'll be kind of the easiest way to do this. So once all of that is set up, we're going to click OK. And it creates for us now a new sheet. So again, right next door is the data. It creates a new sheet. And it gives us a whole bunch of different information here. But what we are ultimately looking for is p-value, right? And here's our p-value. I'm going to highlight that for us. There's the p-value that we need, okay? And that's it. So all of the other stuff, there's other information in here that might be helpful. In fact, there's one number in particular that we're going to use later when we do that Tukey-Kramer test that I mentioned. But I'll talk about that when we need it. But right now, we just need that p-value 0.06. All right, so let's head back to our notes here. So let me set this up now. So now we actually know what the results are and how to do the ANOVA on Excel. Let me actually set up what the process looks like for this. So we would obviously, as always, we'd start with our checks. And in this case, again, we always want to check for random samples. And that farmer did a nice job of dividing up his land and randomly sampling different plots to use the different fertilizers. So it is random. In this case, we want to make sure that each population is approximately normal. Okay, so that's one unique check to this, that each population is approximately normal. Now, how you check that is you'd literally have to do like a dot plot or something like that for each one of these. So I would do a dot plot of those 4 values. I would do a dot plot of those 4 values. Now, these are very, very small sample sizes, right? So obviously, it's going to be a little hard to tell, but what you'd want to make sure is that there are no like significant outliers, that your data is not clearly skewed, things like that would clearly point to something that is not normal. But that is one thing you need to check for. The other thing that you'd have to check for is that the populations have the same variance. So we want to make sure that the populations have the same variance. That's that standard deviation squared, sigma squared. Now there's 2 ways that you can look at this. There's what's called balanced and what's called unbalanced. Okay, there's balanced and unbalanced. So of these 2, let me finish writing this before I get ahead of myself. Unbalanced. Okay, of these 2, you need one of them. All right. Balanced simply means that your sample sizes are equal. That's our case. If we look at our sample sizes, all of our sample sizes are 4. They're all equal. We have a balanced situation. We can say that they have the same variance. If your sample sizes are unbalanced, which is to say that they're not the same or equal size, what you would do is you would take your largest standard deviation. This is why I have that standard deviation column. If we needed it, we could use that. We would take our largest standard deviation. We would divide that by our smallest standard deviation. And we'd want to make sure that that number is less than 2. So in other words, if you look at your largest and smallest standard deviation, you just want to make sure that the largest is not more than twice the smallest. Okay. If they're not, then you have then you pass this check. All right. So those are the 3 checks. Random sample, check that you've got normality. Again, you're basically looking to make sure that there's no outliers or significant skew in your data, that the populations have the same variance, either through same sample sizes or, again, dividing those standard deviations and making sure that it's less than 2. All right. All checks out for us. So now we get into our hypotheses. So again, kind of like the chi-square, we're not going to reference specific values here. We're just going to say that the null is that there's no difference in effectiveness of the fertilizers. that whether he uses fertilizer A, B, C, D, E, whatever one he uses, it's not going to make a difference. They're all equally going to give him the same crop sizes. The alternative then is that there is a difference. So there is a difference in effectiveness. Difference in effectiveness. Okay, so again, in Excel, you want to use ANOVA single factor. Writing this down, both for the reader to know how we got the information, but also for your sake to just kind of remember which one you want to use. And from that, we get a p-value of 0.0, I think it was 0.061 if we rounded it, which is clearly, in this case, greater than the 5% alpha value. So in this case, we would fail to reject the null. We would fail to reject the null. In other words, there is not convincing evidence. There is not convincing evidence that a difference exists in the effectiveness of the fertilizers. In the effectiveness of the fertilizers. Okay. So that's the ANOVA test. Now, I'm going to do a couple more examples just to make sure we've got this down. And again, for the last one, I'll dive into the Tukey-Kramer test and show how that works. Okay. All right, let's take a look at our next example. So in a study conducted by G. Fredrickson of the Colorado School of Mines, 4 welding fluxes, which is powder used to weld together metal parts, with differing chemical compositions were prepared. 5 welds using each flux were made, and the hardness of each weld was measured in Brinell units. The higher the number, the harder the weld. The results are shown. Okay, so we've got 4 different types of this powder and 5 different samples for each. We've got the sample mean and sample standard deviation, which we don't need to do this, but again, would need it if we did the Tukey-Kramer test. Or if it's unbalanced, again, you'd need the standard deviations. And here, even we can see, even though we are balanced, even if we were not balanced, the largest standard deviation is not more than twice the smallest. So we'd be fine either way. All right. Is there convincing evidence of a difference in fluxes at the 5% significance level? All right, let's go ahead and let's actually formally set this one up first, and then we'll go to Excel and actually see what the results are. So we've got our checks. So again, we want to make sure that we've got random samples, which we do. We have, again, if we just look at the data, if you look at each row, look at the data in there, maybe that 239 is a little low compared to the others, but I'm gonna say that these appear to be approximately normal by just visual inspection. So each population is approximately normal. And again, we have a balanced situation here. And so that tells us that our populations have the same variance. Okay. All right, so our hypotheses. There is no difference. So we always for our null, we assume kind of that there's not a difference or things like that. So in this case, there is no difference between the fluxes. Again, we're looking at how hard that weld is when it's done. In this case, there wouldn't be a difference in hardness between those welds. And then the alternative is that there is a difference. Okay, I'll just say there is a difference in the fluxes. Oops, pen got away from me there. There is a difference in the fluxes. All right. Okay. So again, we're going to go, I'm going to show this, but we go to Excel. We're going to use the ANOVA single factor. And let's go ahead and do that. All right, so let's go ahead and pop into Excel. And I've got the data already pre-populated here. And again, we're going to go to our Data tab, find Data Analysis over on the far right, and we want the ANOVA single factor. Now, again, having already done one example, when we go to this, we're going to see that it's already set up for that example, so we do need to make some changes here. So for our input range, we are going to change that now. One less row, one more column. And we still have a group by rows, so at least I do. And I'm using labels in the first column. Again, you wouldn't need that. And where our alpha is still 0.05. So all we needed to really change was just the range. Going to click OK. That's going to populate it into a new sheet. And again, we can see that our p-value is 0.029. All right. All right, so let's go back to our notes. And P was 0.029, which is less than 0.05. So in this case, we do reject the null. We reject the null. There is convincing evidence. There is convincing evidence. Convincing, can't spell that. Let's try that again. There is convincing evidence. Sometimes my brain gets ahead of myself. That a difference exists, or however you want to say that. Difference exists between. Now, again, in this case, we don't know if there's a difference between all the fluxes, if there's just a difference between two of the fluxes. So what we tend to say here is that that exists between at least two of the fluxes. Because that's kind of all we can say, at least two of the fluxes. We can't really get into any more detail than that, okay? So that's where the Tukey-Kramer rule comes into play, all right? So I'm gonna get into that now, and we're gonna talk about, okay, so we found a difference. There is some difference in these four fluxes. We just don't know if, again, is A different than the others? Is B different than the others? Are A and B different than the others? Tukey-Kramer, that's going to tell us where those differences lie. So in the Tukey-Kramer test, what this does is it compares two populations at a time. So in our flux problem, which we're going to use for this example, I can compare A with B, I can compare A with C, A with D, B with C, B with D, C with D. And to find the differences, to figure out where those differences are actually occurring, I have to test all of those different combinations, because even when I run into a difference, it doesn't mean that it's the only difference. So if I want to know all of the differences, I have to test all of the combinations. So with that said, if I'm going to do this test, with four populations, one example, not too bad. If this is kind of part of my job, I'm getting software that's going to do this for me, right? I'm purchasing statistical software that can do this test without having to do all the finagling that we're about to do. You can kind of rig Excel to do some of the automated work for you, but that's a little bit tricky. So let's talk about how this works then. So first of all, there is a table that we're going to use for the Tukey-Kramer test. It's called the Tukey-Kramer table. All right. And I'm going to just kind of walk us through the steps first, and then I'll actually take us into the table to do that. So the first thing we need to do is we need to find a value in that table. So we're going to find a value in the Tukey-Kramer table. All right. And the way that we find that value is we're going to cross-reference two numbers. We're going to find K, which simply refers to the number of populations in our problem. So for us, we have for the fluxes, saying one thing, writing another. Number of populations. So in our problem, we have 4 populations, A, B, C, D. And we also need a value for V, which refers to the total number of samples. So all the samples from all the populations minus the number of populations. So those are the 2 values that we need. So for our case, K is just simply going to be 4 because we have 4 populations. And V, each of those populations had 5 samples. So we have a total of 20 samples in this problem minus the 4 populations. So V is 20 minus 4 or 16. All right. So we're going to go to the table now and I'll show you what that looks like. So this is a Tukey-Kramer table. It's not real exciting. It's just literally a bunch of cells with a bunch of numbers. What I want to point out, though, is you have to be very, very, very careful when you go to find this kind of a table online. Every single table is tailored specifically to a particular alpha value. We are using alpha equals 0.05. I need to make sure that this table is for that alpha value. If we were going to use alpha equals 10% or 1% or 3%, every single one of those would have a different table with different values in it. So just be very cautious of that as you know, if you're using something other than 5%. All right, so you'll notice on this one, K is across the top, V is down the side. And so our number of populations is 4. So we're looking down this column. Our V value, is 16. So there's the row that we're looking at. And so cross-referencing those two, our value is going to be 4.05. Okay. So our value from the table, 4.05. All right. What does that mean? Absolutely nothing right now. Okay. We're gonna kind of set that on the back burner. And we're going to come back to that because what this value is it's a value that we are going to compare against as we now start to get into the kind of the meat of the Tukey-Kramer test. We're going to find a bunch of values and compare those values to this one to determine the pairs that are actually different from each other. Okay, so now we actually go through and we run the test for each pair. Run the Tukey-Kramer test for each pair. And I'll say for each pair of populations just to be specific and clear here. So again, we're going to do this for A and B. We're going to do this for A and C, A and D. Then we're going to do B and C, B and D, and C and D. So technically we have to do this 6 different times. And again, for a small population, that's not too bad. I certainly wouldn't want to do this with any more than that. You add another population, and you're getting into a lot of combinations that you have to test. So we are going to find a test statistic, and I'm going to give you some formulas, and then I'll show you where to get some of this information. It's the absolute value of x bar 1 minus x bar 2. Remember, x bar refers to the sample mean. So it's the difference of the sample means. Okay, remember up in the table, I gave us a column with the sample means. That's why I have that, because we're going to need that for this test now. We're going to divide that by the square root. And I'm going to cut right to the chase here. There's more to this formula. I guess maybe I should give this just in case you'd ever run into the situation. The full formula is what's called the MSE divided by 2 times 1 over N1 plus 1 over N2. Okay, that's the full formula. All right. For our purposes, because our sample sizes are the same, they're all 5. N1 and N2, those refer to the sample sizes for the two pair, or for the pair of populations. Because those are the same, you end up, if those are the same, I end up with just kind of 1 over N plus 1 over N, which is 2 over N. Well, MSE over 2 times 2 over n, those 2's just cancel. So that entire square root part can be simplified when your sample sizes are the same across all the populations. We can just simplify that denominator to the square root of MSE divided by n, the sample size for one population. Okay, that's an n. All right, so that's how we find the test statistic. That's the value then that we compare to the 4.05 to determine whether or not there's a difference between the two populations that we're testing. Now, what is this whole MSE thing that I keep talking about? Let me go back to our spreadsheet here. And MSE is a number in our spreadsheet. When we did the ANOVA test, it's this number right here. Okay, let me actually highlight that. We want home, there we go. All right, it's MS, and then it's within groups. Let me expand this out. It's within groups. So it's MS, and within groups, that's what you're kind of cross-referencing, and that's the number that refers to the MSE. Okay, it's basically a standard error. It's like a standard deviation. All right, so let's go through then and see how this actually works. So we are going to take, we're going to start with A and B. And so A and B, if we go up and look at our values here, A had a mean of 253.8. B had a mean of 263.2. Okay, so we are going to take the difference of those two. It technically doesn't matter what order you go in here because, again, we're going to take the absolute value. So whether it's positive or negative, it's just going to come out positive anyway. So for that reason, I always just kind of drop the absolute value and just do the larger minus the smaller just to ensure that it's positive. So I'm going to take 263.2 minus 253.8 divided by the square root. Again, that MSE was 63.975 divided by, in this case, the 5 in our sample size per population. That gives us a value of 2.63. Okay. And what we do now is we compare that number to 4.05. If the number we just found is bigger than 4.05, that's where the difference lies. If it's smaller, like in this case, because this is less than 4.05, then there's no difference, no statistical difference between those two populations. That's not what caused caused us to reject the null. So we go on to the next pair, and let's try A and C. So again, for A and C, I look at my means. So A, again, that mean was 253.8. C was 271. And so we do the same process. So you can kind of see where you might be able to kind of automate some of this using like even Excel if you typed in some formulas and things like that. But generally speaking, like I said, if I'm going to do this at all on any regular basis, I am going to find some kind of statistical software that can just do this for me. All right, so that's our setup, difference in means. The bottom, the denominator, is not going to change for any of these problems. So in this case, we get 4.81, and that is greater than 4.05. That tells me that this is at least one pair in our populations that has a difference. So there might be others, but that definitely contributed to why we rejected the null and determined that there was a difference among the populations. All right. So I think you probably get the idea from here. I'm going to just give the values for the remaining ones. So we have AD, BC, BD, and CD. So those would be the remaining pairs to test. Again, you're just setting up that same formula over and over and over again. If we did that, AD would be 2.29. BC is 2.18. BD is the smallest at 0.34, and CD is 2.52. So in this case, what that tells us is that all of those are less than 4.05. The only difference that occurs in those populations is between A and C. Okay. So that is the Tukey-Kramer test. Again, it just simply takes the ANOVA test, the results of the ANOVA test, and allows us to then actually drill down into where the differences lie between the populations. All right, that takes us to the end of this lesson. Chi-square, for goodness of fit, ANOVA, and then kind of deeper into the ANOVA, the Tukey-Kramer test. I hope that was helpful, and I hope to see you in our final lesson. Take care.